All right, thanks, Ben. All right, I'm very excited that we have Dr. Zhang to kick us off with our first invited talk. Dr. Zhang is a partner engine manager at Microsoft Cloud and AI. He received his bachelor's and master's from Tsinghua and his PhD from Carnegie Mellon. He's an IEEE fellow. The program has a long list of his accomplishments, but today he's going to be talking to us about visual document intelligence in the wild. And I'm very excited to learn more about both the OneOCR papers work as well as LayoutLM and all the new products that Microsoft's building around the document intelligence area. So take it away, Cha.
Thanks, Sandeep, for the introduction. Hello, everyone. So today I'm going to talk about OCR and document understanding. I'm Cha from Microsoft Cloud and AI. Next slide. So within Cloud AI, I'm part of this cognitive service, which is essentially a set of pre-trained and customized models with a REST API interface. Usually, it has four major pillars. There's vision, there's speech, there's language, and there's decision. And for today's presentation, I'll be mainly talk about two APIs within cognitive service. There's the read API for OCR, which extracts text from images, from PDF files, from documents, and also provide text line bounding boxes, and that be used for post-processing of any other applications. We also have a form recognizer API, which is our document understanding thing, which essentially extracts not just the text, but we also extract document structure like tables, selection marks, fields, values, and other intelligence. And the main application of these two are for process automation, knowledge mining, and industry-specific applications. So let's jump right into the OCR part. OCR has been a research topic for many, many years. I think recently, with the mobile kind of popularity, the input to OCR becomes more wild. It used to be only black and white scan or fax images, but now we're talking about natural images captured by phones. So the challenge of a universal OCR for all these possible inputs, including like street view, product label, poster, business card, slides, etc., are actually much more difficult than previous black and white document images. So first, there's a huge, large scale variability across all these images. Text lines in these images tend to have very large aspect ratio. So this is in contrast to object detection, where usually 1:1, 1:2, 1:3 kind of aspect ratio is sufficient for capture most objects. But for text lines, it can be 10:1, 20:1 kind of aspect ratio. Many of these text lines in natural images tend to be not axis aligned, and so they can be skewed, they can be curved even. And how do we detect those kind of text reliably is a big challenge. We also have the challenge of very small size text lines nearby, say, a large text line. In such case, the interlying space could be very small, and how do we do this reliably? Is a challenge. We have very complex, ambiguous layout, and we have text line like background, like fences, bricks, and stripes. And fences, believe it or not, is very easy to confuse with a string of ones, for example. So how do you tell that these are not actually characters? The localization accuracy for OCR is also very high. In typical object detection, IOU greater than 0.5 is usually sufficient, but for text lines, even 0.9 accuracy is probably not enough, because if you miss 1 or 2 characters, you just got it wrong for the OCR part. And the resolution of the input image need to be maintained at a very high to avoid excessive small text instances. So this diagram shows the flow of the read API. So take an input image. Our first step is to run text detection and take the text detection result. We normalize and rectify and normalize the detected text lines into standard height but variable length images. And then we run a character model and language model to decode the text out of these images. At the end, we also build a rejection model to improve the overall to reduce the false positive rate and get the final results. And I'm going to go into more details in the upcoming slides. So just dive one level deeper. Take the input image, the text detection algorithm first, run a anchor-free region-based proposal network based on text segment detection. I'll talk more in detail later. And then we run a relation network based on line grouping to group these text segments into lines. And then after non-max suppression, we get these text lines. And you can see that it's not just straight text lines, we also get these curved text lines very accurately. So this is sort of the network architecture for anchor-free region proposal network for text segment detection. And so take an arbitrary input image. We first run a vision backbone, and let's say it's a ResNet 50. We take, so ResNet 50 has pooling layers that will reduce the resolution across multiple layers. And so we take these layers output from different resolution and run a feature pyramid network to produce a set of feature maps at the different resolutions. And at the different resolutions, we run basically a dense box detector to extract text segments. And here, by text segments, we really mean these small green bounding boxes here. And so each one is sort of a small portion of the text. And so the algorithm, the basic algorithm here is essentially, you can consider this as a per feature point or per pixel classification, whether this belongs to text or not. And then take any of these text feature points, you can run a regressor to estimate the small bounding box, essentially trying to get the top and bottom of the text line for regression. And then we have steps later to combine these. So you can see out of this previous step, we get a bunch of text segments like this. So they are sort of variable size, but they roughly capture the text line shape. And the next step would be, how do you connect these segments into actual text lines? And so here we propose an approach called relation network. And so the idea is take nearby text segments that have been detected in the previous step. We run a relation network, which essentially takes two of these segments, extract visual features out of them, and then takes the union of these two and extract visual features, concatenate all the features together, run a convolution network, and then you make a decision whether these two segments should be connected or disconnected. And with that information, you can group these text segments into lines. And this is what we get in the end on the right. Let me see if I can. Okay, so the main advantage of using a relation network compared with a traditional, say, rule-based Stacklink approach is that it looks beyond just the decision whether it's text or non-text. So take this bottom image as example. You have this Tony's cable car, but this black and white image is what we get sort of as a textness score map. And you can see that when characters are sparse, you have these connected connections here. And so in order to be able to figure out that these are actually belong to the same text segment, the relation network, because it takes visual features to estimate whether two segments shall be connected, will consider, for example, textures will be similar, background similar, and then it realize, oh, these should be connected. And so you get results like this, which is much more complete than if you just look at this and through rules, it's very hard to say, well, these are actually should be connected. It's much more robust this way. A few additional examples. On the left it was a traditional algorithm called the Stacklink, and you can see that we have a few broken text lines, especially like the bottom, the BMW, the 3 characters are pretty far apart. And with the relation network, we're able to connect them and just create a single text line out of it. Let me show you a few additional examples, and this is on a small data set called SCOT CTW 1500, and you can see that the algorithm does really well, not only on straight text lines, but also curved text lines. And one additional challenge that we have for OCR is the challenge of detecting small text in high resolution images. As I mentioned earlier, one thing for OCR as a challenge is that we need to maintain the image at a very high resolution in order to make sure that these texts are not resized to a size that cannot be recognized. But internally, we still have to set a certain resolution. And so if the image contains really, really dense text, then after resize, you still have the issue of some of the texts being too small, let's say below even 12 pixels height. Even human would have difficulty recognize these texts after resizing. So if you run the typical text detector, you end up with result like this, which is not very good. So the proposal that we have is something called region-wise adaptive scaling. And so you take an input image, you run first a stage text block detection and trying to figure out where are the text blocks are. And so here, for example, these are some larger text and here are some small text, and for each text region, we actually estimate their scales. And then we scale them adaptively into a larger text blocks, and then we run detectors on top. And so this is a pretty straightforward approach, as probably about 30% computation into the OCR engine, but then the result is it's capable of detecting text of different sizes, and even with very tiny text, we were able to do them reliably. Here's an example after the adaptive scaling. So once the text lines are detected, these text lines are normalized into a rectangular shape where the height is usually fixed, and then the width of the image is going to be depend on the text line, how many characters or words in the text line. So it's a variable length input image. And so the idea of the text decoder is to decode this image into real text. And the network architecture is pretty standard nowadays. You take this, run through a CNN feature extractor, you end up this elongated kind of feature map. And then you cut this feature map into small frames, and each frame is like a feature. And so you treat that as the input of a deep bidirectional LSTM model. And then you run through this DBLSTM, add a softmax layer, and then you run through a language model and the weighted finance transducer, a state transducer decoder, and you get this actual text line. Another challenge that we have is to expand the language coverage of the OCR engine. So take an input image. Today, we're able to basically run a universal text detector, which means our text detector is, it doesn't matter what kind of language you have, it's the same detector. One single model handles every language. And so that follows the text line detection and the relation network approach I mentioned earlier. But the text decoder part is actually separated into different scripts. Here scripts For example, CJK, Chinese, Japanese, Korean is one character model. Latin, all the Latin languages is one character model. Arabic is one character model. So this allows us to rapidly expand into many different languages. And so these are grouped language character models with a universal text detector, and we output all the JSON results. So the Reader API today is available both in cloud and on-prem. So take a HTTP request in with an attachment, a stream of input like an image or PDF file or TIFF file. You provide the customer API key, you call analyze, and it will return operation ID, and then you go take the operation ID and fetch the result. And so this is pretty standard for asynchronous API call for OCR. Just to show you some of these results. So this is an example of a mixed language image, which contains many different languages. And you can see that the advantage of us running a universal text detector is that we are able to detect all these texts without being aware of what language it is. And then running through different scripts, classification, and language models, we're able basically to run the character model and language model per text line. So that gives us the capability of handling images with different languages. Let's say even you have 10 languages, we're able to handle it. Basically, we'll handle it per text line for one language. And then let me show you a few examples of the result for the Reader API. So just going through them quickly. So you have standard documents and documents like a curved text line with some curved text lines. You have images in the wild. So this is results from the API. So it does pretty well on images for product labels. And these are all kind of documents. And so you can see that, and including a handwritten note here, receipts, text lines of different orientations, and etc. Additionally, more documents here. And then visuals, additional visuals. And so this one contains mixed languages. So that's sort of, it can handle all these cases really well. So that's sort of the brief coverage of the OCR engine, the Reader API. Moving forward, I will talk about our form recognizer API, which is mostly targeting for document understanding. So the form recognizer API contains three major components. There's a layout API, which is sort of the foundation of form recognizer. So in addition to extract text, layout API extract the layout of the documents. Currently, the two main features that we're adding is a table extraction and the selection mark extraction, which are usually very important for many of these pre-built and custom things that we do on top of layout. And for pre-builds, we have a few pre-builds today that includes pre-built invoice to extract 26 invoice key value pairs plus line items. We have receipts, and we have invoice ID models, and then we have business cards. And then we also provide a customization capability for customer to process any arbitrary input forms through model training themselves. And so today, I will not talk much about the layout on the table part. I think later on, there's an invited talk about table processing. It's definitely one of a very interesting topic. And we do have a state-of-the-art table detection algorithm in the layout API. And we'll mostly talk about how we build these pre-builds and custom. So this is sort of a typical language understanding problem. And so this is a form. I think this is a mixed language. It's an application form for income tax convention. I think it's in Japan. One thing you notice is that not all the documents can have a very clear reading order. And so just take this, like, how do you define a good reading order? It's not easy even for human. So the question is, how can we extract reliable knowledge such as key value pairs out of this without a reliable key reading order, which is typically very critical for traditional language models like BERT to work well. So in this domain, I would first say that actually there's a lot of explorations in the computer vision community in the past few days under these visual linguistic topic. And that includes things like visual question answering, image captioning, image text retrieval, referred expression comprehension, and visual common sense reasoning. So these are all very hot topics recently for computer vision community. And I'm listing some of these representative works here. Majority of them are sort of depending on either BERT language model and combined with visual features. Nowadays, I think the visual information also can be extracted with transformers. So you have a unified architecture for doing this kind of visual linguistic processing. But without going into details for those visual linguistics works, let's focus a bit more on documents. And so documents is somewhat different from these visual linguistic works, at least the type of input is different. And so we have quite a few existing works on this. Some of the popular approaches, such as graph neural networks, which is sort of very naturally, and because you think of these text lines with bounding boxes and you say, well, nearby text lines should connect. And so this is like a graph convolutional approach. And then there are other approaches that use relation classifier or multi-scale classification, etc., to do document parsing. The approach that I'm going to talk about today is actually probably quite famous in this community. It's called the LayoutLM. So the full name is Pretraining for Text with Rich Layout and Style Information, published in last year's KDD. Input of document understanding can be this report, form, receipt, invoice, all kind of different shapes. It's actually very complicated. So just give an example. Let's say we want to extract information out of invoice. The invoice, we want to know what's the date, what's the invoice ID, what's the number, what's the address, what's the name, what is the item list. So you can see that they all scatter around in the document, and it's sort of structured, but if you look across many different invoices, the structure is hard to describe. So this is kind of a problem we're trying to address with the LayoutLM approach. So the architecture of LayoutLM is actually quite straightforward extension of the BERT model. In the traditional language model like BERT, basically the input is encoded as text embeddings, and then you run through a transformer, and then you can use that pre-trained model to fine-tune for downstream tasks. In LayoutLM, we added two simple things. One, we directly embed the position information, the 2D position information of bounding boxes of text lines. So that add x0, y0, x1, y1 are very straightforward, but it does provide spatial information, 2D spatial information into the model, so the model can learn about these spatial relationships. Additionally, I think the first LayoutLM model takes in some image embedding, which is coming out of a fast RCNN feature extractor, which takes all these text line bounding boxes, regions for extracting these features. And then it's a combination of these image and layout embedding for downstream tasks. And so this is, I guess, one of the early works on a transformer-based approach for document understanding. And it's becoming really popular nowadays. And then in ACL 2021, this year, we published a work called LayoutLM v2 with a bunch of additional improvements. So first, we have managed to embed the image features directly into the transformer layer and side by side with the text. And so you take a rendered image of this document, you run through some visual encoders like a ResNet, and then you do a pooling layer to get all these feature maps, and these feature maps now get directly embedded into the input for the transformer layer. We also have a slight modified self-attention mechanism. So in addition to the typical sort of text-only self-attention, the transform layer of LayoutLM v2 includes self-attention, a modified formula that considers also the 1D and 2D spatial relationship between text lines. And that certainly improves the capability for the transformer layers to understand better these spatial relationships of the input. And then on top, in terms of the training target, in addition to the traditional mask visual language modeling that's being used in the LayoutLM, we added two loss functions. One is the so-called text image alignment, in which we added a task of masking a few text lines in the image and trying to use this model to predict whether the bounding box is covered in the visual image or uncovered. And so that's additional training task one. And then we have another additional loss function, which is the text image matching. Takes a random image and a random text input. We decide to train, well, are these two the same from the same document or not? And so these are the two additional pre-training tasks for LayoutLM v2. The pre-training data is on the well-known IIT CDIP dataset that has about 11 million scan document. And so the process is you run the OCR first, you get all these text lines and bounding boxes, and then you run through these LayoutLM or LayoutLM v2 models to train as pre-training to get these models. And these models are then evaluated based on their downstream tasks. So in this particular example where we talk about semantic entity recognition, we have a few examples like form understanding or receipt understanding or document information extraction, let's say from NDA documents. And you can see from the table that first, the LayoutLM model outperformed the traditional language only based model quite significantly because of the added spatial information. And then the LayoutLM v2 additionally has reduced the error rate probably by sometimes nearly half, sometimes about 20%-ish. And so it's still a big improvement over the LayoutLM v1. Here's another task of document image classification. And you can see that again, LayoutLM and LayoutLM v2 both work very well on this particular document image classification task. And lastly, document VQA. So this is to answer questions out of based on documents, and you can again see that document the LayoutLM v2 does really well in this particular task. In fact, as December 22nd last year, 2020, it was ranked the top approach for the TextVQA leaderboard. Okay, so this is a kind of a question being asked, like what is the zip code, what data is seen, etc. So we have on one side we're developing the research for LayoutLM. On the other side, we are rapidly putting this LayoutLM into production, and so you can see that. The model came out somewhere in KDD last year. And then by last August, we have our pre-built invoice model that's totally based on LayoutLM. in private preview. And then when it went to public preview in November, and then this March, we have the receipt model in public preview based on LayoutLM. And then in August this year, we have built a LayoutLM based generic key value extraction model for that. So let me show you a quick video. Can you see the hear the audio?
Yes.
Okay.
To show that the algorithm does not rely only on text cues to block the net amount data, the system is still capable of extracting total. In the next example, we capture the same invoice with a mobile phone. Notice the paper is heavily scrunched. This challenges both the OCR engine and the field extraction algorithm. And our system handles both very well. In the last example, we performed an extreme task with a folded invoice. Most of the visible fields are still extracted correctly.
Yeah, so that's how the capability of the preview invoice model. Okay, so just to conclude, first, I think a universal OCR engine is really within our reach. The engine is so powerful; it handles both document and image in the wild very well. All that needed seems to be some representative training data that can be used for training these models. And some scalable computing platform and training tools. Just recall that we have a universal text detector, and then we have these script-based language models. By the way, the read API also supplies information whether the text line is a handwritten or a printed text line. We are also at the beginning of document understanding, which is becoming a really hot topic for vision and language cross-field research. So combining visual and language information certainly is a very powerful idea, and it can be applicable to many downstream document understanding tasks. We definitely need more researchers on a number of topics. Actually, many of them are in the layout part, which we didn't touch. Things like how do you do table structure recognition really well? How do you extract page objects, tables, let's say charts, diagrams, equations, etc. And then how do you use these LayoutLM models for better customization that includes how to reduce the number of documents needed for customization. So these remain to be very challenging topics. And that's all for my presentation. Just a few links here if you're interested for the read API, for form recognizer, and there's an email for contacting us. Thank you.
Well, awesome. Thank you very much, Cha, for that very interesting talk spanning both OCR and FormRec. I think we have a few minutes for questions. So please unmute yourself and raise your hand before you speak.
Hi, I had a question. Okay, go ahead.
Oh, go ahead.
Regarding a single language detector, why was that decision? Was it just simpler, one single model for all languages for our, because our languages are similar? What were the reasons to have one single text detector for any language?
Yeah, I think the goal certainly is to reduce the engineering overhead. And so if you're building a real product, you want the pipeline to be as simple as possible, and having a single text line detector would make everything a lot simpler. We did actually have a lot of doubt at the beginning whether this is possible. But I think over time, we have build our confidence over time that, yeah, this is doable. A single detector is capable of detecting all languages, including like Arabic, Hindi, some of these languages that looks very different, but the universal detectors seem to handle them really well.
Thank you. Yeah, that's impressive.
Dave, you have a question?
Is the same text line detector used for scripts that are written vertically as scripts that are written horizontally?
Yes.
So, and do you have to detect, say, which type of script it is? Because if I think to me, like, say, looking at a page of Chinese characters written vertically, I mean, there obviously is a horizontal alignment too, that if you didn't know that you were supposed to be looking vertically, how does it know which to do?
So, so there are some internal kind of details regarding detecting horizontal and vertical text lines, and so the text detector at the bottom, when you run these features to decide whether text segments are text or non-text, this is kind of universal, and relation network is universal. But then I think there's a few post-processing steps trying to estimate a text line should it be decoded in a horizontal way or vertical way. Typically, this is easy if the text line is long. Like, okay, so if you have a few words in the text line, it's very easy to see, well, that should be a vertical line, this should be a horizontal line. When it's a single character, it's much harder because, for example, Z, when you rotate and say, well, this is a horizontal text, it can be recognized as an N character. And so that's like, these are some confusions that will depend on contextual information. So you look at nearby text line to decide, oh, this should be a horizontal text line. So yeah, there's some small kind of detail that we need to pay attention to solve this.
Thank you.
Next question, Saurabh Rawat. Saurabh, did you have a question? I see a raised hand.
Hello, can you hear me?
Yes, please go ahead.
My audio was disconnected. Thank you, Chair, for the great presentation. I had a question around LayoutLM, particularly around the kind of the intuitions behind using visual information and how much impact it actually brings in, especially with the representations that are actually top down rather than bottom up, meaning very broader level, global level at the image. So can you share intuitions and the impact that visual information has on document intelligence?
Yeah, the visual information, I think if you read the papers, I think through ablation study, we do see advantage of using the visual information. You can, if you think about LayoutLM, what it takes is basically text information and bounding box information. So thinking deeper, the bounding box information in some way captures some of the visual part. Let's say how big the font is. And so that, based on the height of these text lines, you sort of know, oh, this looks like a bigger text line, and this looks like a small text line. And so some of the font information, the size information are embedded into or captured into the basic base layout with the position encoding. But I think additional information such as font, such as the visual color, the background color, and all this information does require this visual embedding to capture. And so we do see that visual information helps in improving the accuracy of LayoutLM.
A follow-up on this one, do you see any concerns? Because one of many of the representations that I've seen in this literature are not exactly grounded at the token level. For example, like the two-stream architecture that we use at LayoutLM, the two streams are completely disparate, and so it's basically to the model to actually start aligning them. So do you see that as a challenge, especially when we are looking at features that we expect to be really for aligned text, right? Like font and so on, boldness and so on and so forth. So that, do we see that as a challenge in these models, and how are you guys evaluating that? Yes, indeed, this feature is being done.
Yeah, so I think particularly when we work on things like invoice, we do have all these. So for example, a boldness of a font in the invoice typically means there's some kind of header information, and then the fields are likely not. And so what we observe is that, yeah, the model captures well of this information to the point that you don't need to pay attention to this. So it looks like if you just put in the text, put in the bounding box and some visual information, it just extract them. So internally, we do not fully understand how the model learned this, whether these information are actually not that important. Maybe the spatial information is enough, or the model somehow captures it. We haven't been able to really understand deeper. And this, I guess, one of the big issues that we still need to work on, which is how do we improve sort of the understandability of these models to debug, at least like for debugging purpose, like to understand why if sometimes it fails. So yeah, it works well. It's not perfect. I think there's a lot of additional work to do.
Thank you.
I think we have one more question from Hamid.
Thanks, Sandeep. Thanks, Jeff, for the great presentation. So on line grouping, you mentioned that you basically use a relation network. I'm wondering, how do you train this? Do you train this as basically with the ground truth of the whole page, or adjacent words, as you are showing some boxes, just 2 characters from the left word and the right word? So I didn't quite get that part.
Okay. So that has something to do with how we label the ground truth. And so I know some of the academia OCR data set label the ground truth at word level. And there's certainly benefit of doing that at word level. But I think in terms of the cost, in terms of labeling these images at word level, it's significantly more expensive compared with labeling the text lines. And so text lines, you basically draw a polygon that cover many words, 10, 20 words. And so for our model training, we train, our ground truth is at text line level. We're not at word level. And therefore, sort of the text line level annotation naturally provides the information whether words should be connected or not.
I see, but still OCR need to basically capture the words together, so that at the same time.
Yeah, the word information is obtained through the character model decoding. So when we decode these words, we have a rough position information of where a character happens and where the space happens. That through this DBL-STM model, that we actually being able to derive word bounding boxes from the decoder.
Okay, thank you very much. Thanks, John.
Mm-hmm.
Any other questions? All right, I'm going to try and squeeze in one last question before we move over to the first session of papers and posters. So one of the things I noticed in the form recognizer is like in the product side, you've already released 2, sort of like an invoice and a receipt product. Do you have any thoughts on when we will get to sort of the same sort of results that we're seeing in extremely large language models like GPT-3, where we could have like really good few-shot learning performance, where we say, I'll annotate like 5 receipts, and then that's your receipt model, because we could do prompted in context learning for these sorts of models. Are we like super far away from that? Do we have a shot of getting there?
No, I don't think so. I don't think we're very far away. I think so. Of course, GPT-3 kind of trained on billions of texts. I think the training data that we have for LayoutLM is still smaller, but it's not difficult to increase the size of these training data in the sense that you don't really need any human label in there. Like you basically run OCR, which is, you already have an OCR engine, just run it. And then you train these LayoutLM models directly. And so I do see that in the future, it's easy to expand the size of the training data to make the model much more capable over time. And in terms of the number of training examples required, actually today's custom form part of form recognizer, we do take only 5 examples for training. And you get a pretty decent results out of that. Of course, I think customers want 1, they don't want 5, they just want to go down just 1 example for training. So we still have a lot of challenges there, but I think we're not too far away. Yeah. So we're not like, it's not like we need hundreds of examples for training. No, we're talking about just 5 or 10-ish examples to train a pretty decent model.
Sounds great. Thank you. Any other last questions? If not, you'll get another chance to listen to Cha later this evening during the panel discussion.
Thank you. Thank you, Sandeep.
Thank you very much, Cha.